Alright, so here we are back for part 2 of Who's Got Gas. And so, last time we learned about the three stooges of the gas world. Larry, Curly, and Moll, otherwise known as Boyle, Charles, and Gay-Lussac. And they're great laws, and they serve a great purpose, but the problem is, very rarely, if ever, can you adjust pressure and volume and not have it affect temperature, okay, at least in the real world, or adjust pressure and temperature and not affect volume, or volume and temperature and not affect pressure. And so we needed a rule, we needed a law, a formula, something to work with that would allow us to deal with gases kind of a little bit more in the real world, where all three criteria are changing. And so what we did was we said, well, if they're all in these relationships and they're all kind of similar, then let's just throw all three formulas together. And so we combined them together, and what we got was the combined gas law. And so the combined gas law is just the three other laws put together. Okay, so you've got Boyle at the top here, P1, V1, P2, P2. You've got Gay-Lussac with P1, T1, P2, T2. And you've got Charles with V1, T1, V2, T2. And so you stick them all together and you get P1, V1 over T1 is equal to P2, V2 over T2. And really, if you're doing any gas law stuff, this is the formula you want to use. Because even if temperature stays the same, so these two stay the same, if you divide them out, okay, T2 is going to end up over here, or T1 is going to end up over here, and they're going to cancel each other out anyways. And so rather than remembering three separate laws, or four separate laws, including this one, just remember this one and kind of work from there. Okay? And so down here you've got your list of what everything means, which you're pretty familiar with that already. And so, here's your example. A helium-filled balloon at sea level has a volume of 2.1 liters at 0.998 atmospheres and 36 degrees Celsius. If it is released and rises to an elevation at which the pressure is 0.900 atmospheres, so the pressure went down, and the temperature is 28 degrees Celsius, the temperature also went down, what would be the new volume in the balloon? And so I've got all my information listed out over here. Pressure in atmospheres, the volume in, it should be liters, not kilopascals, and my unknown volume. And then my temperature, 36 degrees Celsius plus 273, gives me 309 Kelvin. And my second temperature, my final temperature, 28 degrees Celsius plus 273 again, gives me 301 Kelvin. So stick that into your formula. You get 0.998 atmospheres times 200, or 2.1, that should be liters, over 309 Kelvin equals 0.9 atmospheres times x over 301. And so you readjust it to solve for x, and what you're left with is 2.3 atmospheres. And again, if you're not sure about your math, always look at your units. Atmospheres should cancel, Kelvin should cancel, and if I'd written this in correctly as 2.1 liters, I did all kinds of things wrong on this one. If I wrote this in correctly as 2.1 liters, then I would have wrote it incorrectly down here at 2.3 liters. And so this is a good example of why, A, you shouldn't do chemistry at 1 o'clock in the morning. B, you should always check your units. And C, you should double check your work after that. So, correct answer here would be 2.3 liters if you have liters correctly here and here, as it was given to you in the question. Okay? But that's all combined gas law is. It's the same stuff that we used yesterday, combined into one formula to make it easy to remember, because that's what we need. Easiness. And so, in moving forward, once we got this combined gas law, Avogadro came back into the picture, and he was really working this whole mole angle, okay, his whole 6.02 times 10 to the 23rd thing. And so he did a bunch of math and a bunch of experiments, and he came up with what was called Avogadro's principle. Okay? And basically he said, if I have two gases, okay, and they have equal volumes, doesn't matter what the gas is, and it's at the same temperature and the same pressure, they're going to have the same number of particles in it. Okay, and so he did a whole bunch more math, and he found out that there was such a thing as a molar volume. Okay, molar mass was the mass of one mole of something, so molar volume is going to be the volume of one mole of any gas. And so he did have to stipulate a little bit there, because that volume is at what's called STP. And STP, while it is the racer's edge and all that good stuff if you're a car guy, in chemistry, STP stands for standard pressure and temperature. And so anytime you hear STP, you can immediately think 1 atmosphere of pressure and 0 degrees Celsius. Okay, or if you want to go Kelvin, you just think 273. Okay, so standard temperature and pressure is kind of those basic criteria. And so any gas that's at this pressure and this temperature is going to take up 22.4 liters if you have 1 mole of that gas. Okay, that's what Avogadro did. So what can we do with that? We can combine it with what we know from our previous dealings with Avogadro, where we can say if I have a certain number of how many grams of carbon dioxide gas are in a balloon, that has a volume of 1.0 liters, and again, very important, it's at STP. Okay, and so what we do, we solve this like a regular kind of stoichiometry problem. I have 1 liter. I know my molar volume is 22.4 liters per mole, because I'm at STP. And so that gives me moles of carbon dioxide. And I know my molar mass of carbon dioxide is 44 grams per mole. And so when I do the math, 1 divided by 22.4 times 44 even, gives me a mass of 1.96 grams. Okay. And so I can use volume to help me figure out how much of something I have. And again, there's a quiz. This one's due Thursday before school. Get it done, get your points, and we'll talk to you tonight or tomorrow night. Have a great night.